Hello everyone, my name is Professor Mega. How old are you today? Every living thing has a specific age. But did you know that stars like our sun have age too? Every single star scattered across the universe has a life cycle. So, how did the life cycle of stars work? Let's start our adventure now through the galaxies. Huh? Stars have life cycles? They're not even a living thing. Let me show you. Just like I mentioned, every star has an age. Our sun now is 4.5 billion years old. It is currently in middle age and needs to go through a life cycle. In the life cycle of a star, there are different stages, just like us. We go through childhood, teenagehood, and adulthood. Stars too, they born and die just like us. Aboard Mega 101, let's blast off into outer space and explore the life cycle of a star. Into the galaxies. How do stars form? The birth of a star is the first stage of its life cycle. In space, there are enormous clouds of gas and dust known as a stellar nebula. Hey, I see one drifting in front of me. It grows bigger and bigger until it's extremely massive. Due to strong gravity, the dust cloud collapses, folds in, and gets hotter and denser. This forms a protostar, which is the hot core formed by the dust. As the newborn protostar therefore begins to generate heat, hydrogen atoms in the cloud collide and fuse together to make helium, just like how blue and yellow are combined to make green. This chemical reaction, or thermonuclear fusion, causes the star to become very bright, just like our sun. Then, the protostar transforms into the Titari phase, a pre-main sequence star as time flies by. The Titari phase is one of the earliest formations of the star, and it is cooler and does not contain enough temperature in order to ignite. Then, the star begins its main sequence, the longest part of its lifetime. About 90% of stars are main sequence stars, just like our sun. The duration of a star's main sequence depends on the star's type, usually ranging from 10 million years to 10 billion years, but surprisingly, some low-mass stars can have 1 trillion years of their main sequence. During the main sequence, radiation, or energy that comes from a source that travels at the speed of light and heat, protecting the star from collapsing due to gravity. What happens during the rest of its lifetime depends on how massive it is. After the main sequence, the star slowly runs out of hydrogen fuel and is close to death. It expands and swells so big that it can swallow up surrounding planets. They measure from 62 million to up to 620 million miles in diameter, 100 to 1,000 times wider than our sun. They even have a surface temperature of 5,000 Kelvin. Wow, surprising, isn't it? But let's not explore red giants. We'll be melted into ice cream in just less than 1 second. So scary. Professor Mega, what if the sun became a red giant? Great question, kids. Let's travel through time into the future. If the sun became a red giant, it would swell up so big that it would swallow up Mercury, Venus, and even our planet Earth. All 3 planets will burst into flames and sink into the blazing plasma of the sun, in which all life will come to an end. Ah, I'm so scared. It's okay, kids. It won't happen until 5 billion years later. That would be 200 million human generations from now. Then, something amazing happens. The burning star, after falling down due to the pressure of gravity, scrapes off its outer layers, causing it to shrink. The shredded outer layers then forms a planetary nebula. Wait, what's a planetary nebula? A planetary nebula is gas forming in a ring shape around a dying star. Planetary nebulas can be in various colors, especially in bright hues of red, blue, and green. Most are blue-green in natural color. Professor Mega, why do planetary nebulas have so much color? Hold your curiosity and I'll explain. Planetary nebulas are glowing, beautiful gas. They are so colorful because they are composed of many different colored elements, such as carbon, nitrogen, hydrogen, helium, and oxygen, the element we inhale 22,000 times every day. But what's happening to the star in the center of the nebula? The star, which now is a carbon core, finally begins to cool down to about 3,000 degrees Kelvin. This is the beginning of one of its ending stages, which is so-called a white dwarf. White dwarfs are known for their glowing and white and light blue color. Even though it is cooler than a red giant, it is still cooler than itself in its main sequence stage. So, it's a white dwarf going to stay white until the end of its life? Nope! As millions of years pass by, it slowly begins to cool down even more, entering the stage of the black dwarf, which is the opposite color of the white dwarf. A black dwarf's temperature is way cooler than a white dwarf, under 6,000 Kelvin. But why is a black dwarf black? Haha, that's because it no longer generates heat or light, so it turns darker and darker until it's black. But what about for more massive stars? Right, for the stars that are extremely gigantic, they face a complete tragedy. Instead of shredding its outer layers to form a planetary nebula, their outer layers explode and burst into deep space like a popping balloon, scattering its pieces everywhere. This is a supernova explosion. Some supernova explosions send off a blast of gamma ray, the strongest, most damaging stage of light in the electromagnetic spectrum. Oh, sad. The star has exploded and ended its life. Wait, not yet. One more stage. This last stage is the black hole. It is triggered by the supernova explosion. Can you believe it? A black hole is one of the most extreme known objects in the observable universe. Its gravity is so strong that whatever is near it, even light, gets sucked into total darkness. Back to Mega 101. Today, we have learned about the life cycle of stars. Can you remember the stages? Protostar, Titori, main sequence, red giant, white dwarf, black dwarf, and then explodes as a supernova or becomes a black hole. Huh? Why is this spaceship so dark? What's happening? Black hole, black hole, black hole, warning.